As I said before, the topic of big O notation deserves a full course on its own. So as long as we are aware of the notation, and when we do the exercises during the synchronous session, then it will become clearer what the big O notation means, and it will hopefully spark some interest. So by the time you take a course on algorithms, you will know what is to come. The next topic is called the integers and division. Now, the integers are of particular importance in the area of information technology, and more specifically in the area of cryptography. Cryptographic algorithms deal with integers, in particular very large integers, but the algorithms for cryptography are general, so it doesn't matter if it's a long integer or a small integer. The algorithms apply equally. So it is important that we understand some properties of the integer numbers, so that when you take a course on cryptography, you will understand the fundamentals of cryptography, which will make things much easier for you. The first thing to consider is the well-ordering principle. And the well-ordering principle says that any non-empty set of natural numbers has the smallest element. And this is kind of obvious. Some of you may even say simplistic, but you will see how useful this well-ordering principle applies when we are using it to prove facts about the integer numbers. So keep this principle at hand, and we'll revisit in due time. The first definition we have here is divisor. So we say that two integers, a and b, b is a divisor or factor of a if a is equal to q times b. So if you look at the division, and then if you have an integer division, let's say 15 divided by 3, then you know that 3 divides 15, right? Because there is a number such that 15 is equal to that number times 3, right? So the notation that we use here is b divides a. So in other words, 3 divides 15. And this means that 15 is divisible by 3, and we say 3 divides 15. This theorem here is very important. So it's left as an exercise to prove, and we'll do that during the synchronous session. But for now, let's just take a look at some of the meaning of this theorem. And let's take, for example, the first part. We're assuming that a, b, and c are integers. So remember, the set of the integer numbers, that includes the positive numbers, the negative numbers, and 0, all integers. We say that if a divides b and a divides c, then a divides the addition of b and c. That's going to be very useful when we are proving other theorems. So again, keep this with a red flag and with a bookmark, because we'll revisit this theorem. Something about the second part, this is important. All integers. So if a divides b, then a divides b multiplied by any integer c. It makes sense. Then we have number 3 is transitivity. So a divides b, b divides c, then a divides c. So by transitivity. This one, number 4, we'll use it in at least I can think now of one proof that we'll do in the future. And it says that if C divides A and C divides B, then C divides XA plus YB. And then look at this. For any integers X and Y, this will be very useful in a number of proofs that we do in the future. So the division algorithm. The division algorithm is basically what describes divisions as we perform them on paper. So if you are dividing A by B, you know that you will have a quotient and then you have a remainder. This algorithm is basically telling you that. Then we have the definition of the quotient and the remainder, which we already know by the regular arithmetic division that we know how to do on paper. So, modular arithmetic. When we talk about modular arithmetic, we are basically talking about integer divisions. Even in a programming language, those of you who are familiar with programming languages, it is possible to perform modulo operations. They are very, very important in the area of cryptography. The definition we have next is congruent. We also call them congruencies. So what does it mean that A is congruent to B? We denote that with this symbol. A is congruent to B. So that means that if M divides A minus B, then A is congruent to B modulo M. Okay? Remember when we talk about the implications and how to interpret implications from plain English? This is one of those cases. You have P if Q. That means Q implies P, right? So don't forget these translations from plain English to logical expressions. In other words, to simplify things and without loss of generality, we can say that A is congruent to B modulo M means that the remainder of dividing A by M and B by M are the same. So that's the definition of a congruency. Keep that in mind. We have a theorem here. This theorem uses a double implication. So that's, remember, that's another way in which you can write a double implication, if with double F. So we say M is a positive integer, A and B are integers. So M is a positive integer, remember, okay? Positive integer. Then M cannot be 0. M has to be 1 or a larger integer. Then A is congruent to B modulo M if and only if, okay, A modulo M is equals to B modulo M. We'll prove that theorem, which basically just follows from the definition of a congruency. We'll do that during the synchronous session. Another theorem here. So M, again, is a positive integer. So the integers A and B are congruent modulo M if and only if there is a K such that K times M plus B is equal to A. Again, we'll prove that during the synchronous. Theorem number 5. And here we're going to use one of the properties in the theorem that I showed you at the very beginning with 4 parts. But for now, let's just take a look at the theorem. It says, again, that m is a positive integer. So don't forget that m has to be a positive integer. Then you have 2 congruencies. A is congruent to B, C is congruent to D. Then the addition of A and C and B and D are congruent modulo m. Also, the multiplication applies as well.